Hi guys, this is Mayank Sharma and the following video is me solving the fourth question for the end-term evaluation for subject mathematical methods 2, that is subject code MAT104. So yeah, let's head straight to the question. So what we have got here is a non-homogeneous linear ordinary differential equation of the form y double dash plus p of x y dash plus q of x y equals rx. So we will be finding the general solution of this equation right here using the method of variation of parameters, and the general solution of this kind of equation is y is equal to y homogeneous plus y particular solution. So first thing first, let's focus on the homogeneous part, and that would be y dash plus ny is equal to 0. We need to solve this. So what we are going to do is write a characteristic equation that would be lambda square plus 9 is equal to 0, and this gives us the value of lambda equals to plus minus 3 iota, and it's visible enough that it is of the form a plus ib a plus I omega, and solution for the solution for the equation of solution for these kind of equation which involves the imaginary roots is given by y is equal to e raised to power minus ax by 2 on the bracket c1 cos omega x plus c2 sine omega x. Visible enough that a is equal to 0 here and omega here is 3, implies that y is equal to c1 cos 3x plus c2 sine 3x. So we have got the homogeneous part of the equation right here, and so let's move on further to find the solution to the practical part of the equation. Moving on to find the value of y practical, what we get is y practical is equal to u1 y1 plus u2 y2, and y1 and y2 here are yh is equal to c1 y1 plus c2 y2, implying y1 here would be cos 3x and y2 here would be sine 3x. Also u1 is equal to minus of y2 times r by w, not like omega is w, and u2 would be integral of y1 times r by w, and these two integrals would be with respect to x. W here is Wronskian, and it is the determinant of y1, y2, and y1 dash and y2 dash. So first thing first, let's calculate the Wronskian. Wronskian here would be w equal to y1, that was cos 3x, and y2 sine 3x, and y1 dash, that is going to be minus 3 times sine 3x, and y2 dash is going to be 3 times cos 3x. What we get, it is w, not to confuse with omega. W is going to be 3 times cos square 3x plus sine square 3x, implying w is 3. Keep it in mind. So let's calculate the value of u1 and u2 too, and let's calculate them in parallel manner, because it's going to save us some space and time, and both are quite important here. So as I said earlier, u1 is going to be minus of y2 or by omega by w, and u2 is going to be integral of y1 times rx upon w with respect to dx. So yeah, u1 is going to be integral of minus times integral of sine 3x, r was cosec x, that is 1 upon sine x. So that's what I'm going to write. 3 dx. u2 is going to be cos 3x upon 3 sine x dx. So expanding sine 3x and cos 3x in the next step, what we get is u1 is equal to minus 3 sine x minus 4 sine cube x upon 3 sine x, and u2 is equal to integral cos 3x would be 4 cos cube x minus 3 cos x upon 3 sin x dx. So now let's focus on u1 right here. What we get is integral of 1 integral of 1 minus 4 by 3 times sine square x with respect to dx, and what we can do is just rearrange a bit. What we are going to get is let's take 1 by 3 outside. What we get is 3 minus 4 sine square x dx. u1 would be 1 by 3 1 plus 2 would be, and 1 minus 2 sine square x. I have skipped a step, that is way too much easy to be understood. And dx, as we know, 1 minus 2 sine square x is equal to cos 2x. We get minus 1 by 3 integral 1 plus cos 2x dx, or 2 times cos 2x. So integrating, what we get is u1 is equal to minus 1 by 3 times x plus sine 2x. Now let's focus on u2. So focusing back on u2, what we get is 4 cos cube x by 3 sine x minus cot x. This whole would be integrated with respect to dx. Let's consider sin x as t. Let's rewrite it in a simple form. That would be 4 cos square x by 3 sin x cos x dx minus, let's write it a bit separately, cot x dx, and consider sin x equals to t. For this equation right here only, consider sin x equal to t. What we get is u2 would be 4 times, let's take 4 by 3 outside here, 1 minus t square cos square equals to 1 minus sin square x upon t and cos x dx, and what we get is cos x dx equals to dt. So that's it. And cot x, the integral of cot x with respect to x. So this is going to be, u2 is going to be 4 by 3 ln t mod t plus minus t square by 2, that is t square by 2 in bracket, we're replacing it back, and integral of cot x is ln mod sin x, and that's it. We are just ignoring the constants right here because we are going to write them anyway. So yeah, just replace back t equals to sin x here. What we get is 4 by 3. So replacing t equals to sin x back, what we get is 4 by 3 ln mod sin x minus sin square, or 2 by 3 of sin square x minus ln mod sin x, and this is will eventually tell us that u2 right here is equal to 1 by 3 natural log of mod sin x minus 2 by 3 of sin square x. So yeah, this is what we have derived so far. So let's move forward and put the value u1 and u2 at the required place. What the place was required was that the y practical was equal to u1 y1 plus u2 y2. So y practical is equal to, y1 was cos 3x times u1, and let's put the value of u1 right here that we have derived. That would be minus 1 by 3 times x plus sine 2x, and u2 times y2, that would be y2 was sine 3x by 1 by, so let's put value of u2, that was 1 by 3 times natural log of sine x, and minus 2 sine square x. And so as we wrote earlier, that the general solution for this particular equation right here would be y equals y homogeneous plus y practical, and we have got y practical here, y homogeneous right here. So yeah, let's write it. Our general solution would be c1 cos 3x plus c2 sine 3x, and let's write the value of y practical right here. That would be minus cos 3x by 3 times x plus sine 2x, and plus sine 3x by 3 natural log of mod of sine x minus 2 sine squared x. And yeah, that's the solution. Could be simplified further, but would be a tedious process at the end of the day. So that's it. That's my solution for this question.